majority of it, obviously, is that probability stuff that we just got done doing. So we will definitely review some more, but quizzes were very good, so I was very pleased with that. So, first thing we're talking about in Chapter 6 is discrete random variables. We have to start obviously with some definitions. If I'm going to talk about something, you need to know what that is. So a random variable, that's just a term that's used for the numerical measure of the outcome from a probability experiment. So it's just kind of like finding the probability of something happening. If it's discrete, then that means it has a countable number of values. So if I wanted the probability of a student in my class bringing a pencil today. Okay, that's a countable number. If I'm looking at this class, it would be some number between 0 and, how many people do we have in this class? 15. So you could count the number of options. Continuous has an infinite number of values. I couldn't count it. So it might be how long it takes you to write down these definitions. Okay, I can't count all the possibilities because it could take you so many seconds or a decimal value. And there's also no maximum because it could take you all day if you're really, really slow. So there is a difference between a discrete and a continuous variable. So here are my examples. The first one, the number of light bulbs that burn out in a room of 10 light bulbs in the next year. Would that be discrete or continuous?
Discrete.
Discrete. We can count those light bulbs. Okay, my possible variables. X could be what values? What'd you say? 1%. Except it could be 0, couldn't it? Because they could all last. I'm not going to write all those out. Can I just list a few and show that it goes up to 10?
Can we just do like a 0-10?
No, because that could possibly include decimals. So list out a few to show me. All right, the number of leaves on a randomly selected oak tree.
It's discrete.
It's discrete. I don't want to go count them, but we could.
Maybe it's a little bit.
Are you sure you don't want to?
I mean, we could spend our day sitting in a tree and counting leaves, I guess. So what would my values of X be?
A lot. 0 to like 3,000.
Yeah. Is there a maximum? No. So I'm just going to put 0, 1, 2, and then dot, dot, dot. It doesn't have a stopping point. It's not like I only had my 10 light bulbs in the room. It could be up to any number. All right. The length of time between calls to 911.
Infinite. Or continuous.
Right. Continuous because there are an infinite number of values that could be. And they would have to be, could they be negatives?
No.
No. Could it really be 0? No, you could always measure that portion of time. So I'm just going to say X is greater than 0. It can be any positive number. All right, so that's like the first question that's going to be on your homework tonight. Just looking at these situations, discrete or continuous, telling me the types of values. Are we okay with that? The probability distribution, we have done that before. You think on that last review, the second review we did, the very last question I think asked you to make a probability distribution, and it was like X could be 1 through 4, and it gave you a formula for the probability. So when I ask you to make a probability distribution, that's really just a table that lists your possible values for X and the probability of each. Now, can I make that if it's continuous? Can I list every possible value of X?
No.
No. So we really need that. It works with discrete variables. I couldn't do it with a continuous one. All right. So let's look at an example. So this would be a discrete distribution. I want to suppose a basketball player is asked to shoot free throws. Create a possible probability distribution for X equals 0, 1, 2, or 3 shots made. So they're going to shoot 3 times. And I want the probability that you make a given number of shots. So if you're shooting 3 times, you could make 0, 1, 2, or 3. go about finding this?
We have to figure out her percentage.
Right, I would need some information about how accurate this basketball player is, right? That would be helpful. Let's say alright, so let's say the probability of making a shot, what do we want to say? How accurate are they?
68.
68% accuracy?
Yeah.
Okay. So, how would you find the probability of making 0 of those throws? What would that be?
1 minus 68. Or 1 minus 0.68.
Well, 68% is just probability that you make one of them, right?
Oh.
Or, sorry, that you make none of them. So if you made 0, you would have to miss all of them. So we are going to be talking more about how you would actually calculate this. Now we could find the probability that you miss all. 1 minus 0.68 is 32, so there's a 32% chance of a miss. So if you miss all 4 of them, you would have, or all 3 of them, sorry, you would have to multiply that 3 times. So we would get
0.0327. 0.0328.
okay. Let's say I want probability, let's jump down here, that you made all 3. What would you do?
68 to the third.
Okay, now then in this 1 and 2, this is kind of the motivation for the next couple sections that we're doing. The probability of making one of them, you could make the first one and miss the next 2. Or you could miss the first one and make the second and miss the third. Or you could miss the first 2 and make the last one. Okay, we are going to be talking about shortcuts for calculating something like this in the next few sections, because you see, when we're only shooting 3 shots, we have this many calculations to do. If you were going to shoot 10 shots, can you imagine how much more complicated this becomes? So we are going to need a shortcut for that. If we did calculate this, we get 0.2089. How could I easily find the probability that you make 2 of them? One and subtract off all the others, right? Because we know that in a probability distribution, it always has to add to 1. So if you're missing one value, you could do 1 minus the ones you have and get the next one. So there you go. That's like question number 2 on your homework. It gives you a probability distribution and it says find the missing value. And we know that in probability distribution, every one of these probabilities has to be between what 2 numbers? 0 and 1, and it always has to add up to 1. Okay. So far, so good? So let's look at some, and I want you to tell me if these are probability distributions or not. So what do I need to check?
Equals 1.
Okay. So are all of these between 0 and 1? Yes. Let's see what it adds up to. So is it?
Nope.
No. Alright, what about this one? Why?
Yeah.
I can't have a negative value. Alright, what about this last one? Yes. If you add those up, they add up to 1. So probability distribution has to add up to 1. You cannot have a probability smaller than 0 or bigger than 1. far so good. This part has all been kind of a review because we talked about all of this in the last chapter. The new thing that we are going to look at, we're going to talk about graphing probability distribution, and then we'll start looking at the mean of a probability distribution. So if I wanted to draw a probability histogram of this distribution, there are different ways you could do it. Usually in this book, they just kind of draw a little line. Your x values would go on your horizontal axis, so we have x equals 0, 1, 2. And then my probabilities would be on my y-axis. So maybe I count by 0.1. And so then if I'm asking you to draw this, you're just drawing either like a bar going up to it, or a lot of times you'll just see like a dot with a line going up to it. So my first probability is 0.06 when my x is 0. When x is 1, we have a 0.58. When x is 2, we have 0.22. 3, we have 0.1. 4, we have 0.03. 5, we have 0.01. So you're just graphing those probabilities. We could look at this and answer questions about the shape of our distribution. Is this symmetric, skewed left, skewed right? Skewed right. Here's my high, my tail extends on that way. When we talked about symmetry, we looked at it with our histograms and we said, well, think about like if you drew that bell curve, you know, it would look like this, so this tail goes really far out to the right. So this is skewed right. Is that okay with everybody? To graph that probability distribution if you need to. Okay. Let's say I wanted to find the mean of this. So we have never done that before, but if you go to your formula sheet, we are now in chapter 6, and the very first thing there is the mean or expected value of a discrete distribution. So the mean is our mu. What does that funny looking E thing mean? The sum. We're going to add up the x times p of x. So it's on our formula sheet. I would like to find the mean for the example we were just doing. So what we will usually do is just add another column to our probability distribution. We already have the x and we have the p of x. So now we have to multiply those two things. So this was our data that we were looking at. we drew our probability distribution for it. So if I need to find my mean, we're just going to add an x times p of x column. So 0 times 0.06, 1 times 0.58, 2 times 0.22, 0.44, 3 times 0.1, 4 times 0.03, and 5 times 0.01. And so then to get our mean, you add all those up. And so we get 1.22, is that about right?
Yeah, 49.
Where did I mistype? Oh, yep, I left off one. 1.49. Okay. So the mean calculation is not too difficult here. You just multiply and add. So does that mean that if I go to a video store, everybody is renting 1.49 videos? No, that's the average. Now, if I go to a video store and they only had, 6 customers that day, does that mean if they found their average, it would come out to be exactly this? No, it's just kind of like when we talked about probability experiments. The more you have, the closer your mean gets to what we expect. So, if they only had 10 customers, it's probably not going to be exactly this. But if we had 100 customers, it would get closer to this. If we had 500 customers, it would get closer to this. So the higher your n is, the closer it should get to this value. This is our expected. Doesn't mean it always works out that way, but we would expect that eventually. All right. So I did have just the definition of that expected value. The mean is also called the expected value because the mean represents what we would expect to happen in the long run. So you might hear me find the mean, or you might hear me say find the mean, or I might say find the expected value. They are the same thing. And your formula sheet says that. It has mean and then in parentheses expected value. So it tells you. So my next example. Suppose a life insurance company sells a $250,000 policy, one-year term life insurance policy to a 49-year-old female for $530. The probability that the female will survive the year is 0.99791. Compute the expected value of this policy to the insurance company. Okay, expected value, we're kind of like finding the mean, right? And when we find the mean, we add up the x times p of x. Okay, so we have to think about what happens here. If this female survives, does the life insurance company make money or lose money? How much money do they make?
530.
Okay, so the x, the value, is 530, and the probability of that happening is the probability that she survives the year, 0.99791. Okay, but what happens if she doesn't survive?
They lose.
They have to pay her $250,000.
Not her.
Well, sure. Survivors. How about that? So it's a loss to them. Now, how much money do they actually lose? Not $250,000 because she did pay them that $530. So how do we find out how much they actually lose? So if she dies, they will lose $249,000 for $249,470. How would I find the probability of that happening? So 1 minus your 0.99791. So there's our probability distribution. So now if we want the mean, we need x times p of x. And then what do I do with those numbers? Add them up. And we get $7.50. So their expected value is $7.50. That means if they go out and they sell 500 of these policies, they are expecting to bring in, on average, $7.50 for every one of them. Because they know sometimes they're going to pay out and sometimes they're going to keep money. Does that make sense? So, expected value is the same as mean. The last calculation we need to talk about is standard deviation for a discrete random variable. So it is, again, just on your formula sheet. The calculation, it's a little nasty looking. There are two ways of doing it. You can take each of your x's minus the mean and square that. Typically, if we're going to do it by hand, we will use the second way because we're already usually doing the x times p of x when we find the mean, so it's not that big of a stretch. It's a little bit easier to calculate. So, what we will have to do is the square root of the sum of the x squared p of x's minus the mean squared. Okay, on your formula sheet, you don't have to memorize it. We just have to be able to do it. So I would like to use the example that we have been and calculate the standard deviation for that. So going back to this probability distribution that we were doing. Okay. So if I needed to find my standard deviation here, we will add another column. And that will be my x squared p of x. Okay, so 0 squared is 0 times 0.06 is still 0. 1 squared is 1 times 0.58 is 0.58. 2 squared is 4 times 0.22, 0.88. 3 squared is 9 times 0.1 is 0.9. 4 squared is 16 times 0.03 is 0.48. 5 squared is 25 times 0.01 is 0.25. Does everybody see where I got that? So your formula, it's a little nastier looking, says you do the square root of the sum of these x squared p of x's. So if I add that column up, you get 3.09 minus your mean, which we found to be 1.49 squared. And we get a standard deviation of 0.9327. If I asked you to find variance, what would you do? Square that. Variance is just standard deviation squared. Are there questions on how I got that value? Let's talk about, last I'd like to do is show you how to do this on the calculator, just like all of our other standard deviation calculations. I like for you to understand how to do it by hand, but if we're going to be doing a lot of these, it makes more sense to use our resources, okay? So I need you to grab a calculator if you don't have one. And what we are going to do is go to our list. So stat edit. And you are going to enter your x values in L1 and your probabilities in L2. So the original probabilities given. Everybody have that?
Which one are we putting out to?
The probability, the P of x from the original. Now what we're going to do is go into our calculate. Get it?
She just forgot the number.
So if we go to stat, calculate, we still want to do one variable statistics because this is not like an x and a y. We're talking about the probability of each thing happening. But when you get here, don't just enter through this. Your list is L1, that's your x value. The y here was our probability, that's like the frequency. So on your frequency list, we need to put L2 there. So to do that, you can just hit second and the number 2, and that enters your L2. So then if you hit enter, it comes up the x bar 1.49, isn't that what we had for our mean? And the sigma, the standard deviation of x, was the 0.9327 that we got. Okay, so you do the one variable calculations, but your frequency has to be set as the probabilities. And then you can get it from your calculator. Alright, any questions there? So I'm done. I'm going to figure out the calculator issue for those of you that are having it. But you